In 1847, a technological triumph was exhibited to the public in St. Gall, Switzerland, where newspaper coverage described a mechanical duck built by a man named Reichsteiner.
After a light touch on the base, the duck, in the most natural way in the world, begins to look around him, eyeing the audience with an intelligent air. His lord and master goes off to look for something for the bird to eat. No sooner has he filled the dish with oatmeal porridge than our famished friend plunges his beak deep into it, showing his satisfaction by some characteristic movements of his tail. After this, satisfied with his frugal meal, he stands up and begins to flap his wings and to stretch himself, while expressing his gratitude by several contented quacks.
What are we to make of Reichsteiner's duck? As a machine, it's clearly a tour de force, a triumph, and a harbinger of things to come. Indeed, the modern world is dominated by machines and the products of machines. As life, however, in spite of the convincing movements, the duck was a ludicrous failure. But why? Why do the universal laws of science, the laws underlying our technology, seem to reveal only a mechanical universe? Why are the laws of nature apparently not the laws of life? Modern science began some 4 centuries ago, and one of its basic assumptions is that nature is governed by universal laws. The 20th century physicist Ilya Prigogine describes how science has relied on the idea of cause and effect.
The basis of the vision of classical physics was the conviction that the future is determined by the present, and therefore a careful study of the present permits the unveiling of the future. At no time, however, was this more than a theoretical possibility. Yet in some sense, this unlimited predictability was an essential element of the scientific picture of the physical world. We may perhaps even call it the founding myth of classical science. For most of the founders of classical science, even for Einstein, science was an attempt to go beyond the world of appearances, to reach a timeless world of supreme rationality.
In other words, classical science is rooted in determinism. Karl Popper, perhaps the greatest contemporary philosopher of science, describes how determinism is embodied in the concept of natural physical laws.
Historically, one can look upon the idea of a scientific determinism as the result of replacing the idea of God by the idea of nature, and the idea of divine law by that of natural law. Nature, or perhaps the law of nature, is omnipotent as well as omniscient. It fixes everything in advance. By contrast with God, who is inscrutable and who may be known only by revelation, the laws of nature may be discovered by human reason, aided by human experience. And if we know the laws of nature, we can predict the future from the present data by purely rational methods.
Newton was the first great scientific determinist. His theory of gravitation established the field of mechanics, the core of classical physics, and it provided a paradigm or model that science has continued to emulate. Newton portrayed science as the study of an orderly, deterministic universe, a universe that's as regular and predictable as a clock. In using this paradigm, modern science has been undeniably successful. For 300 years, scientists have used Newton's approach to stake out new areas of knowledge. But does this success really justify our belief that the universe is deterministic? As early as 1873, the great British physicist James Clerk Maxwell raised doubts by pointing out that the evidence is biased. Astronomer John Barrow describes Maxwell's position.
Those persuaded towards determinism, Maxwell contended, have been swayed in their judgment by the fact that physicists, and especially their public spokesmen, always focus attention upon problems that reinforce the image of the clockwork universe. Their examples invariably possess one very special property. A small change in the starting conditions creating some motion produces only a small change in the final state that results. The false view that all motions exhibit this neat property is what has led to a prejudice in favor of determinism.
The classical determinist viewpoint is very powerful. It has survived even relativity theory and quantum theory, although these developments both produced some important nuances in how we understand determinism. But recent discoveries are showing us that fundamental concepts like determinism and predictability can have meanings radically different from the traditional ones. A conceptual revolution has spread rapidly throughout the sciences, and it has extended scientific thought into realms previously thought to be beyond the reach of science. This conceptual revolution has its roots in 4 separate domains, which we'll discuss at some length. These are fractals, chaos, self-organization, and emergent computation. Each deals with recently discovered or rediscovered phenomena which at first sight seem bizarre and counterintuitive. Fractals, for example, are infinitely complex forms, pathological monster curves they've been called. Fractals have inspired the development of a new branch of geometry. It turns out that this new mathematical language describes, in a natural but rigorous way, the complex forms all around us, things like clouds, trees, and lungs. Chaos, a second element of this broad revolution, involves apparently ordinary mathematical equations that suddenly give random, unpredictable results. The old, more orderly rules of arithmetic are no longer enough. This new mathematics of chaos not only opens up new areas of scientific inquiry, it raises deep philosophical questions as well. Self-organization, the third area of inquiry, is the apparently mysterious process by which complex entities create themselves from simple components without a master plan. Sometimes it's called spontaneous organization because order appears to emerge from disorder with no obvious cause. But the cause of spontaneous order is disequilibrium, and self-organization theory is showing why our world, the world of life, must be a world of constant change. And finally, emergent computation, together with a related area known as artificial life, deals with the logic of self-organization. Research in emergent computation is revealing new natural laws that are, in a sense, the laws of intelligence. It's now becoming apparent that fractals, chaos, self-organization, and emergent computation are linked in a number of ways. They also seem to cohere into a unified system that provides a new, richer, and more open idea of science itself. We'll explore these areas in order to understand the emerging new science of complexity, of order out of chaos, the science of creation. This is the science that will shape our lives in the 21st century.